Hey Justin, good morning. This is Dr. B. We're going to be meeting in about an hour. I just completed the problem set for chapter 2, so I thought I'd give you a recording of it that you might find handy. I'm starting with my handwritten answers to all the problems, which you should see there for 53 through 39. And I should point out what I did was, do you remember last time how when we went through them, we ended up going through, I don't know, 1 through 20 or so. And by the time an hour was done, all we'd done is completed the problems that were in the book for which the answers were given. So you didn't get any real individual help with the problems that have no answers to them. So I went backwards this time. So the problems ended with 53, so I started with 53 and worked my way back. Here's 53 through 39. And if I go like this should give you 38 through 33. I'm just doing this so these are like snapshots, so you can get a quick look at them. And there's 31 through 24, and then the previous problem was 17. But 1 through 17 are answered in the book, so I didn't do those because the book gives you detailed answers. I thought this time we'd focus on the ones that have no answers. Okay, so that's that. Now let's go ahead and work our way back from 53 on back, right? So I'm going to go to the problems here, and let's see. So if I go here, yeah, there's 53. You should see that on the board right there on your screen. And let's go ahead and answer these problems. So question 53 asks you to draw as many resonance structures for various molecules. And they start with this structure here. This is nitromethane, and we want to be able to come up with reasonable structures. Now we have I think I'm going to switch to red. I like red. We have a formal negative charge here. That's not red. And we have a formal positive charge here. In other words, oxygen, if you look at the periodic table, has 6 valence electrons, but if you count the number that it's shared, and by that I mean every time you see a line, only count it as 1, because it's only sharing one of those 2 electrons that form that bond. I count 1, 2, 3, 4, 5, 6, 7. That's an extra because oxygen only needs 6, so we have a negative charge here. If you count the number that are shared here, well, none of them are lone pairs, so each counts as 1. 1, 2, 3, 4, but nitrogen's supposed to have 5, so we have a formal positive charge there. This oxygen is perfectly normal, right? Oxygen wants 6, 2, 4, 5, 6, so that's a garden variety oxygen. 2 bonds, 2 lone pairs. Now for resonance structures, you usually look for this game where you can distribute these charges without breaking an entire bond so that it cleaves the molecule. That's a chemical reaction. For example, if this lone pair went in to form a bond, which it can do, and this one came out putting those 2 electrons there, that is a reasonable resonance structure. Now just draw what you've made, and you'll see that we have nitrogen there. Nothing's changed. We're taking electrons away there, but adding there. There's going to be no net charge here, but we'll count them up just to be sure. And so we now have an O minus here by virtue of the 3 lone pairs. And double bond there. See how we formed that right there? And this oxygen now has 2 bonds and 2 lone pairs. That's garden variety oxygen. And now we've moved that negative charge over here. This may seem crazy, but when they did analysis, they determined that this bond length and this bond length were the same. They were almost like a bond order of 1.5. And this is how they rationalize it. It's really the same as saying this is a bond and a half, this is a bond and a half. This has a little bit extra electrons, this has a little bit of extra electrons, but they always find it easier to say it's the average of 2 structures rather than to do these little dotted lines, things like that. So that's where resonance comes into play, and that's why we do it the way we do. Let's convince ourselves that these charges are reasonable. 1, 2, 3, 4, 5, 6, 7. There's an extra on oxygen. This one, 1, 2, 3, 4, 5, 6, good and normal. This one, should it have that positive charge? 1, 2, 3, 4. Yes, nitrogen should have 5. So extra, you give it a negative charge because electrons are negatively charged. If it's deficient, you give it a positive charge because it's more plus than minus, more protons than electrons for that nitrogen. Okay, so that's one resonance structure for nitromethane. They then did ozone. So this was A. I can see this is moving kind of slowly, but we'll just do it's good to do them carefully. Ozone, the way they drew it, looked like this. And I should point out, Justin, that if you want to go faster, at the beginning of this lesson, I showed you images of the answers to everything, but I thought it might be useful to watch as we do it. They drew ozone, which is O3, this way. You'll notice that ozone just doesn't fit. You're going to have something in the middle, something on the outside. You can't give every oxygen 2 bonds and 2 lone pairs. Try it and you'll see that it's just impossible. So one of the reasonable resonance structures might look like this. This is what they drew. 1 lone pair on that one and 3 on that one. First, let's convince ourselves that this is right. Should this have a charge? No. 2 bonds, 2 lone pairs. 1, 2, 3, 4, 5, 6. Should this have a positive charge? Remember, oxygen needs 6. Count the bonds as 1. 1, 2, 3, 4, 5. Yes, it's deficient. Should this have a negative charge? Yes, 2, 4, 6, 7. So this looks reasonable. This molecule is uncharged overall. Now for drawing the resonance structures, can you see how we can do one of these similar transformations like this and shift that negative charge over there? And can you see how this means takes that lone pair, make a bond, remove that lone pair, and remove that bond and make it a lone pair? So now we have 3 lone pairs over here. Oxygen here has not changed. It's both coming and going. And we have our garden variety oxygen over here now. So doing it a little quicker, this has not changed. This is normal now, but this guy has 7, and these are the resonance structures for ozone. Now, if you were to do something like, oh, I don't know, take that bond right there and move it over to this oxygen, that would be wrong for 2 reasons. Number one, you'd be forming 2 separate substances. You're cleaving this overall. That's a chemical reaction. Resonance structures are never chemical reactions. They're just reasonable ways of redrawing a substance. And also, this thing already has a negative charge, and you want to get 2 more electrons. 2 minus is almost always like no-go. You don't want to make something doubly minus. It's just not a reasonable resonance structure. I should also add, if we're being complete, is that if you're moving a negative charge from oxygen to, say, nitrogen, it's okay, but it's not probably reasonable since oxygen is closer to fluorine and therefore more negative than oxygen. The electrons will naturally migrate towards oxygen, not towards nitrogen. People will show those resonance structures, but they'll probably say something like not a major contributor. Okay, so we just did A and B. Let's go ahead and move on to C, which is looks like this the way it was originally drawn. This looks like diazomethane is the name of this thing. But let's go ahead and just draw it the way the book did. I believe they started with this. And they put no lone pairs on this nitrogen, therefore a positive charge. No formal lone pairs on carbon because it has right now 4 bonds and no lone pairs. That's 4, which is what carbon wants. But here we have 2 lone pairs on this nitrogen. After all, diazomethane is uncharged, so if everything's reasonable, that's what it should look like. First, let's convince ourselves that's right. Carbon, if you drew out those hydrogens as bonds, which I probably should have done, you should see that there's no charge on that. This nitrogen, 1, 2, 3, 4, needs 5, short 1, therefore positive. This nitrogen, 1, 2, 3, 4, 5, 6, 1 extra, therefore negative. And let's do the same game. We'll take that negative charge, and yes, I'm going to form a triple bond, right? Crazy. And here I'm going to put a negative charge on carbon. Not the most reasonable thing in the world, but let's go ahead and do it. And we should end up with CH2, single bond, lone pair, right? A carbanion. This is positive here with our triple bond N, and we still have one lone pair. Okay, so this I think is a fairly reasonable resonance structure, although you would say it spends most of its time like this because nitrogen is more electronegative than carbon. However, this looks okay to me, right? Another thing worth noting is that when you count your bonds as 2 in order to check for an octet, in all cases you really want to have an octet. If you have some larger elements, they can have these expanded octets and incomplete octets. But for HONC, you want to try to keep full octets. And here's what I mean by that. Go back to any one of these, like say this nitrogen here, right? 2, 4, 6, 8. Good. See, I'm counting the bonds as 2. I do have an octet in terms of what it has overall, not just what it's sharing. 2, 4, 6, 8, good. 2, 4, 6, 8, good. So that's the kind of game we need. And if you look at this one, it's 2, then a hydrogen, hydrogen, that means 2, 4, 6, 8. Here, 2, 4, 6, 8. Here, 2, 4, 6, 8. So in all cases, we're maintaining our octet. That's something you want to try to do. And so that's a reasonable resonance structure for diazomethane. This is going quite slowly. I'm 11 minutes in and I've only done one problem, so maybe I'll bounce around a little. I think we could do 51 a little bit quicker by just looking at the problem and identifying what the answers will be. I think I can save this as a full screen snip, and this way I can draw on it. And yeah, I guess so. Yeah, I think I can draw here. So here's what the question says. Identify the acids and the bases in this reaction. Don't forget that an acid is an H plus donor and a base is an H plus acceptor. So for A, it looks like they started with something that's, let me see if I can make this bigger. For A, they started with something that is pretty straightforward. H plus donor, well, there's H plus, so that would be your acid right there. And did methanol act as an H plus acceptor? It did, right? It's got its 2 lone pairs of electrons. They went in and glommed onto that H at the expense of forming a positive charge. So that would be donor, that's your acid, that's your base, right? Now in here, we've got, I don't remember doing this one, but let's go ahead and take a look. We've got acetone and titanium tetrachloride. And do we have any H plus being transferred? No, we do not, but we do have titanium acting as an electron pair acceptor. Can you see how it accepted that electron pair? That means that it's a Lewis acid. So you'd say, yes, Lewis acid there. Electron pair donor, those 2 lone pairs in oxygen, one of them was donated to titanium, and therefore this is a Lewis acid, Lewis base situation. Let's take a look at problem C. We've got cyclohexanone reacting with sodium hydride. This is Na plus H minus. That's hydride right there. So that's a very strong Lewis base electron pair donor. It's got that electron pair. So it's going to grab that hydrogen right there, rip it off as H plus. Here's what it looks like mechanistically. And form a negative charge there. That's actually reasonable. I don't think they get to these enolate anions until later, but I will show you that it's resonance stabilized, right? These things can only form if they are not so naked and exposed, and it is spread out over to that oxygen by that resonance interaction. So this looks like it's acting like a Lewis base. This hydrogen is acting like a Lewis acid in that it's accepting electron pair. What electron pair is it accepting? That one right there from the hydride, right? That is your Lewis base right there. Okay, we now have this substance reacting with BH3, borane, I believe it's called. And what's happening? Well, there is a lone pair here, and it looks like that's going to be your Lewis base, right? And that electron pair is getting accepted by boron. Therefore, boron is your Lewis acid. Nitrogen is your Lewis base, and that looks like how we can do question number 51. I should have paused. Okay, the next one working backwards is 44. So let's get ready for that one. 44. Have a look at the question in the textbook. I'm not going to show it on the screen here. And it shows you to write down the reaction of this molecule here, which is pyridine, which has a lone pair, and acetic acid. So it looks like this. Since it's an acid, that H plus is accessible. It can get removed, right? You'll end up with an oxygen there that is resonance stabilized. And this looks like our Lewis base. It's an electron pair donor, and so it can go ahead and attack. Always start your mechanisms by looking for the electron-rich region, typically lone pairs, right? And so it can attack that acidic hydrogen, forming that O minus, which we call an alkoxide. Since it's part of a carboxylate, we call that formal thing a carboxylate anion. And that should form pyridinium. In other words, nitrogen there, but now with a no lone pair anymore. All right, positive charge, and this has a negative charge because we now have 3 lone pairs on that oxygen. Let's go ahead and draw them all. And that means that this acted like a an acid, and that it donated H plus. This acted like a Lewis base, and that it donated its electron pair, and we would call this pyridinium acetate. This would be a salt. And these things crackle when you mix them together because the reaction is so violent. Okay, that is the answer to 44. Question number 40, I'm just going to talk about without actually drawing the screen. I think you can see this little diamond here that'll help a little bit. It says rank the following substances in order of increased acidity. Acidity means that H plus can be removed the easiest. And Ka measures how easily it can happen. It's literally a mathematical term where the Ka means if you have a really high number, that means that it's happening to a large degree. The equilibrium favors removing it, right? Ka for really strong acids is just infinite. But those numbers end up being, 10 to the minus 6 and things like that. So people like to do the negative log of it, the pKa. So to cut to the chase, if you have a really high pKa, that's the opposite. That means it's really hard to remove that hydrogen. But if you have a really low pKa, like 0 or 1, that's the hallmark of a strong acid. Now, acetic acid's not a strong acid, but it does have a pKa less than 10. So in the take-home message is low number means strong acid for pKa. So your strongest acid would be this one. The next strongest acid, so acetic acid, I mean, you could drink it, but that H plus gets removed pretty readily. This one is called phenol, and that H plus can be removed, but it takes a little more effort. It's got a pK of 9.9. Oh, I should say number 2 is pentane-dione, so that H plus hiding right in here can get removed also with 9. So 1, 2, 3, and then acetone. You can take off that anion, but you need a very strong base to do it, and its pKa checks in at about 19. So once again, 1, 2, 3, 4. Let's see if we can keep rolling to 39. And maybe it'll be more efficient this way. So I'm going to see if I can just move down to 39. Write the products of these acid-base reactions. So sulfuric acid is clearly going to be your acid, so it's going to donate H+. So I'd say the products are CH3OH2. In other words, this acted as a base and grabbed that H+, plus HSO4-. Here we have methanol, which is not particularly basic because it's not KOH. This is just an alcohol. And this, on the other hand, this is sodium amide. This is NH2-, very strong Lewis base here with a minus charge there. So it will pick up that H plus and render the alkoxide. So the answer would be CH3O minus plus Na, Na plus NH3. So it would be sodium methoxide plus ammonia are the two things that would form. CH3O minus Na plus NH3 gas, right? So that would be that reaction. That's a little tougher. Here we have methylamine, and amines are weak bases. You got a lone pair there, so if there is something it can react with, it would. And this is sodium hydroxide. Now, sodium hydroxide, right? But it's actually, I'm sorry, it's not just methylamine, it's methylammonium chloride. So we have a positive charge on that end there. And this is sodium hydroxide. So hydroxide is your strong base. It's going to look for something positive. And if it can grab that hydrogen, you take a look at the answer, and maybe I'll switch over because I want to make sure I explain this clearly. Okay, I went to the trouble of just redrawing the problem, and it shows you this methylammonium chloride here. Convince yourself that we do have a positive charge here, and that we do have sodium hydroxide. For me, I begin by recognizing that this is a strong base. Let's make sure I'm drawing this. Strong base. So that's where I'd begin with. And this thing has a positive charge, which can be alleviated. Always think of minus attacking plus. If it grabs an H plus there and reforms that lone pair, that'll just give us plain old, I'm going to draw it like this, CH3 NH2. Now you just have a regular methylamine, and what did we do? We formed OH minus reacted with H plus, that gives us H2O. And what else do we have? We also have Na plus, kick it around, and Cl minus. We call those spectator ions. They didn't do anything. So that should be what happens when these things react. Moving back to 38, and now I'm just showing you the answer key that I came up with. It might be more efficient to work this way. So this is number 38. And I've set it up so I can draw on it now. This is, they ask you to draw each substance and indicate whether the substances are acids or bases. Now this is aluminum bromide, AlBr3. And when you draw this, aluminum likes to form 3 bonds, and bromine likes to form 1 bond with its 3 lone pairs. So bromine looks nice and normal. I see no formal charges. It has 7 valence electrons and a complete octet, right? But aluminum, have a look at that. 2, 4, 6. We don't have a complete octet. This thing would like to have a lone pair if it can get one. So anytime you see these things, or I just, I've worked with this stuff before and I know it's very reactive. And so this is acting as a Lewis acid. It would like to accept an electron pair. This is ethylamine, which can act as a Lewis base. It does have a lone pair of electrons, and it can be an electron pair donor. This is borane, right? And do you see that that boron has an incomplete octet, so it should be a Lewis acid. HF is hydrofluoric acid, so this is a Bronsted acid right there. This stuff is acidic, but it doesn't actually dissociate that much. It's a fairly weak acid. Now, I did add this little detail that the conjugate base, which is F minus, is actually basic, right? But I'd probably just stay away from that. And this is dimethyl sulfide, which is one of the smelliest substances you'll ever run across. Just like ethylamine, I see some lone pairs of electrons, so this can act as a Lewis base. And so that would be, oh, and there's one more, titanium tetrachloride, right? So this is TiCl4, and this is a metal here. And we've got Cl minus right there. So formally, this is Ti4 plus. So that is a pretty strong Lewis acid. It can seek out an electron pair, and it can react with water to form things like that. So this is acting as a Lewis acid. And that is 38. Maybe we can go ahead and take a look at 34 here since it's shown. And I think they're asking us to draw reasonable resonance structures for each of these things. So this looks like the acetate anion. We have a negative charge there, and we can take that carbanion, take those two electrons, throw them in there to form a double bond, and kick that out to form O minus. And in fact, this is probably a more reasonable resonance structure than this one, because the more electronegative element now has the negative charge. I didn't draw the lone pairs, but oxygen has its normal 2 lone pairs, and now it has 3 there. This should be a formal negative charge, meaning we do have a lone pair there if you like to always draw the electrons. Here's the cyclohexadiene anion here. So cyclohexadiene, see 2 double bonds. And we have a negative charge on this carbon. Can we spread it out? Yeah, here we could spread it out quite a bit. We could take that minus charge, form a bond, kick out that one, and form a negative charge right there. And we can go around the horn and do the same thing. If you wanted to draw it cool, you could take that negative charge and in one mechanistic thing spread out the negative charge from here right to there. But basically these 3 positions for the negative charge are equally likely, right? Because take a look at how similar these are. So that's quite a distributed negative charge there. And hang on. And now I moved back just to the answer key because maybe it's easiest just to look in here. So we did B, and let's take a look at C here. And they're asking for reasonable resonance structures here. There's your positive charge there, and each one of the other nitrogens has a lone pair. So start with either one and form a bond and kick it out to create a lone pair to spread the positive charge to there. Do the same thing with this one, and you can show that that positive charge is distributed equally between those 3 nitrogens. Dimethyl sulfide with a positive charge here, well, we do have a pair of electrons here that can kick in and form a bond there, alleviate that positive charge, and put it on sulfur. But just about anything else you try, you cannot get a charge over here. You know, you might be tempted to try to take this bond and throw it on there to make carbon positive, but recognize that you've cleaved the bond if you do that. So this is about all you can do with the dimethyl sulfide cation. Now here, it's very similar to the problem B in that we should be able to distribute this positive charge pretty easily. If you take that double bond, move it almost like a windshield wiper over to there, you'll put a positive charge on this carbon. Similarly here, we'll put a positive charge on this carbon. So we have a very highly resonance delocalized positive charge here for this kind of thing. I hope you're seeing the game that you have like these, what they call conjugation, alternating double bonds makes for lots of resonance structures. Okay, I'm going to move down to 33, and they're asking if it's resonance, yes or no. And they drew a structure that they thought might be a resonance contributor to here, but if you take a close look at it, that bond is broken. When you break a bond completely, it's no longer resonance, it's chemistry. It's actually chemical reaction, which resonance does not do. Resonance is likely alternative structures for one substance. This would be formally a different substance. Here we have the enolate anion, which sure, we could take that double bond there, throw it out there. Notice we have not broken this molecule in 2. It's still one molecule, and we can do that. And for this one, where we have lots of alternating double bonds, yeah, there's ways you can go ahead and distribute it to that carbon, a negative charge there. It would give you the resonance structure shown in so we did C first. Sure, if we put a negative charge there, that's resonance. And in D, if we throw the negative charge all the way down there, which is what they did, that's a resonance structure, absolutely. So now I'm on the 3rd page of the answer key, and you know, just to try to make this fit in a reasonable time, I think I'll stick with this, and that way at least you'll get some exposure to the individual problems. So in 31, I'm seeing this structure here. Hang on. And they're asking for formal charge on each atom that's in red. So if you actually draw this thing out, one lone pair on oxygen looks kind of funny, doesn't it? And it looks like if you draw each of these methyl groups, that's what a CH3 is, you're going to see you have 3 bonds on oxygen and a lone pair. Count up the electrons, you'll probably see you have a positive, 1, 2, 3, yeah, probably a positive charge there, which means the boron would have a negative charge. Let's go ahead and take a look at the answer here. Yes, have a good look at this. And sure, oxygen's positively charged. 1, 2, 3, 4, 5. It's one short. Boron, which is in the aluminum group, which only has 3 valence electrons. If you draw each of those lines, count them as 1. We have 1, 2, 3, 4. That's an extra. So that would be the formal charges on oxygen and boron. For this substance, if you draw it out, you'll see you have a lone pair there, so it should have a formal negative charge. 1, 2, 3, 4, 5. That's one too many. This nitrogen, you'll see it has a positive charge because it's 1, 2, 3, 4. That's short. This nitrogen has no charge because it's got 5 valence electrons that it's sharing, as it should. Here's form C here. Carbon is looking good, just 4 bonds, no lone pairs, so that's no charge. This nitrogen only has 4 valence electrons, needs 5, so a positive charge. Take a look at this one and convince yourself 1, 2, 3, 4, 5, 6. There should be a negative charge there. Ozone we've already done, but let's go ahead and convince ourselves that we have a positive charge here because we need 6, but we only have 1, 2, 3, 4, 5. And this oxygen has a negative charge, 1, 2, 3, 4, 5, 6, 7. Looks reasonable. Methylphosphine, something like that. All right, let's take a look at this thing. We have a lone pair on carbon, which is pretty rare, and it usually leads to a negative charge. So 1, 2, 3, 4, 5. We'll put a negative charge there. Phosphorus is in the nitrogen group, so it normally has 5 valence electrons. Let's count them up. 1, 2, 3, 4. It's short one, positive charge on the phosphorus. And finally, this is called pyrididium oxide. That nitrogen had a lone pair, but it glommed onto oxygen, so now it only has 1, 2, 3, 4 valence electrons, therefore positive charge. Does this oxygen have a negative charge? 1, 2, 3, 4, 5, 6, 7. Supposed to have 6? Yes, negative charge there. 28 I had to look up, I remember. I started writing an explanation, which I suppose might have gotten some partial credit, but there's a better answer. They're asking, why is this substance more polar than this substance, even though chlorine is pulling electrons away? Well, it's true. At first look, it looks like you got negative charge over here. Chlorine's getting pulling electrons away. We're partially negative here. Chlorine's partially more negative than electronegative than carbon, so partially negative there. Oxygen's more electronegative than carbon, so partially negative there. Wow, that's a lot of partial negatives there. Compared to this guy, which, hydrogen is not particularly anything, and therefore oxygen here has a formal negative charge. The thing is that, check this out, it's evenly distributed. So when it's evenly distributed, it renders the molecule overall nonpolar because the negative charges cancel out, if you will. Carbon tetrachloride is a nonpolar molecule. Even though it's got negative charges partially on every single chlorine, they offset each other. Therefore, this is more symmetrical, therefore not as polar as formaldehyde. 26 says, is there a dipole, yes or no? Well, this is good because it kind of applies here. Let's look for that case where you have equal and opposite electronegativities. Here it's only on this side of the molecule, so polar. Here they're both on the right side of the molecule, so polar. Here we're getting close to offsetting, but I'd want a 1-4 relationship for it to really be offsetting. So mostly negative charge up on the top, so still polar, perhaps less than this one. But here you go. Here we have equal and opposite polarities, so this would be a nonpolar molecule. Last problem. Let's see. What are they asking for? Let me look it up. It says identify the most electronegative element in each of the following molecules. Well, nothing beats fluorine for electronegativity, right? Except if you had maybe a formal negative charge on that element. And none of these do except this one down here. So here we've just got chlorofluoromethane. That is one of the chlorofluorocarbons, which has been banned because it's putting a hole in the ozone layer. But fluorine is the most electronegative element, so I'd circle fluorine. Similarly here, I just see fluorine and bromine, and if you take a look at this thing, nothing's funny about it. Every carbon has its reasonable 4 bonds, and there's no formal negative charge or anything. Therefore, fluorine wins here. Here it looks like, once again, if you draw it out as a nice structural formula, you'll just see that there's no formal negative charges or anything, and it's a question of considering nitrogen versus oxygen. Oxygen is right next to fluorine, so it's more electronegative. I'd circle the oxygen. But here, if you take a look at this thing, this looks like dimethyl ether anion. There is one this carbon here is connected to lithium. Now that's a metal, so that's very positive. You'd have a formal negative charge here, right? That's what ionic compounds do. They transfer electrons, metal to nonmetal. So there you have a negative charge on that carbon. That beats everything. So I'd say that carbon is the most electronegative element in the molecule, beating the oxygen because it has lone pairs. It's more electronegative than carbon, but that's a carbanion. That's got a formal negative charge, so that carbon wins. All right, Justin, all the previous problems, the answer was given in the textbook, so I didn't even look at them. And that was a detailed look at all of the problems that did not have solutions to them. Hope that helps.